So this is lecture, what is it, 17 now? 17, Math 331 problem solving. So today is integration day. I know people might be celebrating a different holiday, but it's really integration day. If Kayla had not stayed in my office, if she had come down, I would have played, I think, Coronation Day from Frozen. I don't know if you guys are sick of that movie yet. So what I want to do is I want to do 3 different integrals, and each one illustrates a different technique. And I've posted some integration problems that appear on Putnam or Putnam type exams, and I will draw some homework problems from them. This is not just a technique because we need to do something. These techniques are also extremely useful, and in terms of analytic number theory, for instance, when you want to deal with something like the Riemann zeta function, a lot of these ideas are what we need to prove the functional equation, which starts a lot of the analysis. Okay, so I'm going to hide the names of the techniques first. So here's my first integral. I'm integrating from 0 to pi of e to the cx cosine x dx. What is the first thing you should do when you see an integral? First thought. Okay, that's in terms of attacking it and trying to solve it. So integration by parts is a good way to attack this. When I write down an integral, what's your first thought when you see it? So I could give you the integral from 0 to infinity of e to the e to the e to the e to the x to the x. Let's do x plus 1 to x plus 1 to the x plus 1 dx. All right. What's your first thought when you see this? Yeah, it doesn't converge. It blows up. So the first thing you should do whenever you see an integral is see, does this integral make sense? Is it finite? So here, there's far too much growth. Another issue you could have is, 1 over, x to the 2017. And now this integral is far too small near 0 to make sense. So there's no need to try to figure out this. If I gave you something like the natural log of x divided by x, this is a little bit harder. As x gets very, very large, what does this look like? Or give me a lower bound for this as x gets really large. So it is going to 0, but we need now some idea of how quickly is it going to 0. So when x is very, very large, can you give me a function either smaller than this or larger than this? 1 over x. So we know for large x, this is greater than 1 over x, and the integral of 1 over x diverges. So this integral will diverge. Diverges as greater than or equal to 1 over x if x is greater than or equal to e. So I don't even have to worry about this. Unless, of course, I decide to change the infinity to a 1. And now that I'm only integrating to 1, all right, that's gone. I don't have to worry about how slowly or how rapidly this function is behaving at infinity, because I'm no longer going to infinity. The danger now is what's happening near 0. Is this function integrable near 0? So what's the limit as x goes to infinity of log of x over x? I'm sorry, as it goes to 0, thank you. Limit as x goes to 0 of log of x over x. Okay, given that there's a pause and no one is bursting out answers.
I think it would be 0.
Okay, what rule could you try to use to figure this out? So if we use L'Hopital, the limit of the quotient is the limit of the quotient of the derivatives. What's the derivative of log of x? 1 over x. The derivative of x is 1, so this would be infinity. So the question is, are we allowed to use L'Hopital? What are the rules to use L'Hopital? What do you have to have? You have to, so L'Hopital, what indeterminant? Infinity over infinity or 0 over 0. And I don't care if you want to throw in some signs of plus or minus infinity. As x goes to 0, x goes to 0. But what does natural log of x go to as x goes to 0? What does it go to? It goes to negative infinity. I can't use L'Hopital here. I have negative infinity over a small positive number. What should it be going to? It should be going to negative infinity. So if I used L'Hopital here, I would actually make a mistake. And L'Hopital would be telling me it's going to positive infinity. It's actually going to negative infinity. So this is all wrong. This actually goes to negative infinity. As it is negative infinity over 0, it is not L'Hopitalable. If you try to use that in Scrabble, I am not responsible if they do not give you credit for it. All right? It's good to make these things verbs, adjectives, whatnot. All right. However, we might be able to still deal with this. What you can often do in integration like this is you can take a limit as epsilon goes to 0. And now in something like this, everything is fine and finite for each epsilon. And then I'll take the limit as epsilon goes to 0. So I realize what I'm doing right now is I'm giving you a crash course in general integration theory, and then we're going to go and turn to these problems. So let's try to look at what happens. So we'll call I epsilon the integral from epsilon to 1 of natural log of x over x dx. Any thoughts on how we could integrate this? Yeah. It's a u substitution. If u is the natural log of x, then du is 1 over x dx. Yeah, so I like to go very slowly. As x goes from epsilon to 1, u is going to go from the natural log of epsilon to 0. And it's a little bit of an overkill, but I find it's nice to write these down so that I do not make any mistakes in terms of the bounds. So this would then become the integral from the natural log of epsilon to 0. And now I'm going to have u du. So this is going to become u squared over 2 evaluated at 0 and natural log of epsilon. So I would get negative natural log of epsilon squared divided by 2. Right? And as epsilon goes to 0, this goes to what would this go to as epsilon goes to 0? Negative infinity. So unfortunately for this problem, the blow up is so bad at 0, it's no longer integrable. So whenever you have a problem, an integration problem, you always want to look at how rapidly is it growing. Is it decaying fast enough if you're integrating over an unbounded interval so that things will converge? And then if it has places where it's blowing up, how quickly is it blowing up? This is a really bad blow up. If I had made the blow up a little bit better, I would be okay. So then the question becomes, what could you do to make the blow up a little bit better? Well, if I change the exponent from x to maybe 0.9, that would be enough. And then what you could do is you could get a function that's larger than this. If I had a 0.9, I could do natural log of x over x to the 0.9, I think would be less than or equal to 1 over x to either. Do I want the exponent to be a little bit larger or a little bit smaller? I have a small number. I want to make it small. I think maybe 0.95. And then this will be integrable because the exponent here is less than 1. So when I integrate that, it would be about 0.5. And we should, of course, probably have things like absolute values because the natural log is negative. And what I'm using is that if x is really, really small, I can bound the natural log of x in terms of powers of x and 1 over. OK. I'll do one last integration thing because we were talking about splitting the integral up from epsilon to 1 and taking a limit. And there's just one little warning I want to give you. So if you had control of mathematics and you could write the laws of mathematics, you don't, by the way, not even close, but if you had control, what would you choose for the derivative of a product? Or at least what would your younger selves have chosen? Product of the derivatives, right? If you had a choice, you would have made that choice. What would the derivative of a quotient be if you had a choice? Right. And 1 over cosine of x, what would you choose to call it? I would choose to call it cosecant of x. I think it's absurd that cosine goes with 1 over cosine goes with secant, and 1 over sine goes with cosecant. This is a notational issue. If we wanted to, we could change the world and make people use cosecant for 1 over cosine. This is within the realm of possibility, especially if some of you become extremely rich. Okay? We can publish new textbooks. These ones, however, are a very different structure. These are not right. A lot of good math contest problems are find all functions f and g that satisfy relations like this. When is the derivative of a product the product of the derivatives? One of the results you would love to have in mathematics is the limit as n goes to infinity of the integral from, say, 0 to 1 of fn of x dx equals the integral from 0 to 1 of the limit as n goes to infinity of fn of x dx if the limit as n goes to infinity of fn of x equals f of x. So this would just be the integral of f of x dx. We would love to have a result like that. Does that seem a reasonable result? The integral of a limit is the limit of the integral. So then the question might be, what kind of functions would this hold for? Is this true if f and fn are continuous? Continuous and differentiable. C infinity, that means infinitely differentiable. What do you think? So if I assume my functions are infinitely differentiable, can I interchange the limit and the integral? I'm working on a nice bounded interval. How many of you have taken measure theory? So measure theory deals with issues such as this. And there's a whole series of rules as to when you are allowed to use this interchange. Interchanging operations is one of the things we love to do in mathematics. One of the big techniques of integration is switching the orders of two integrals. Over here, what I want to do is I want to switch a limit and an integral. Do you think it's always possible if my functions are continuous and differentiable, or even infinitely differentiable? So, am I stating this because I want to warn you that it's not always true, or am I stating this because I want you to have this in your arsenal? How well do you know your professor?
You wrote warning.
I did write warning, so that is a really good word to look at, right? This is how you do math contests. You look for key words. There was a chess problem we looked at Math Puzzle Night this week where it was, Can you determine if white has promoted a pawn? And because they're asking it, there's supposed to be an answer to it. So the answer must be yes, we can determine. And in fact, a pawn must have been promoted, because if a pawn has not been promoted, there's no way we can argue, well, maybe the pawn was promoted and then killed because we can't see it on the board. White only had 4 pieces left, a king, 2 pawns, and a bishop. So it turns out white actually promoted a pawn, made it a bishop. And by looking at the board, it's impossible that that was one of the original bishops from the game. And you could go backwards and deduce that. But because it was being asked, you knew there had to be a clear answer. And it couldn't be, I don't know. So given that there's a warning here, let's look at the following. Let's define fn of x as follows. Here's 0, here's 1, here's 1 over n, here's 1 over 2n, and here's I'm sorry. What I want to do is I want to take an interval of size 1 over 2n on each side. So this is 1 over n minus 1 over 2n, and this would be 1 over n plus 1 over 2n. So I have something of width 1 over n at 1 over n. It doesn't hit 0, it doesn't hit 1. And then I'm going to define my function to be a triangle with height 2n. So what is the area under this triangle? Well, it starts over here, goes straight up with the maximum at 1 over n, and then straight down. So it'll be an isosceles triangle. Which is, so the area is 1. So the integral from 0 to 1 of fn of x dx is always 1. What is the limit as n goes to infinity of fn of x? For any fixed x, what is the limit? So when you look at these sequence of functions fn, choose any x. What is the limit of fn of x going to be? What do you think? So what can you tell me about a typical value of fn of x if n is large? What do most values look like? I'm sorry? I'm not talking about the area. I'm talking about the function fn of x. Fn of x is a triangle. It starts at n minus 1 over 2n, goes all the way up to an enormous height of 2n, and then comes all the way back down to 0 at 1 over n plus 1 over 2n. So in this region, I have a triangle. What do I have every place else? Nothing. I have 0. So you give me any value of x. I choose n so large that 1 over n plus 1 over 2n is less than x. Once this triangle moves past x, can it ever move back and get to that x? No. So what is this limit going to be at all x between 0 and 1? It'll just be 0. If I start off at 1, it's 0. And I've always chosen these triangles so they never hit 0, so it's also 0 at 0. So the pointwise limit of this function is always 0. So each of these integrals is 1, but this function is identically 0. This does not equal the integral from 0 to 1 of the limit as n goes to infinity of fn of x dx, because this is just 0. So this tells us we have to be extremely careful. What went wrong? So in mathematics, whenever you have trouble interchanging operations, usually the problem is there's an infinity at work. Where's the infinity in this problem? I've got a bounded interval. Where's my infinity? Yeah, I'm sorry?
No, 1 over n goes to infinity.
Well, no, 1 over n goes to 0. I'm getting smaller and smaller intervals.
Like the value of fx though?
Yes, the height to n. The height is going to infinity. These functions aren't bounded. If you were to add in bounded functions on 0, 1, then you'd be okay. And you might say, well, this function is not differentiable. I can always smooth things out at the edges. That's not a problem. So the issue is that it's unbounded. And that's what causes the problem. As an aside, how many of you know Fubini's theorem about changing orders of integration? All right, I'm seeing people shake heads. All right, so I will actually then just do Fubini's theorem, and then we'll actually talk about how to evaluate these integrals, just because it's worth seeing. So Fubini's theorem. So if and I'm going to just do an easy version. If a to b, c, let's do it this way. X equals a to b, y equals c to d of f of x, y, absolute value, dy dx is less than infinity, then the integral from x equals a to b, integral y equals c to d, f of x, y, dy dx equals the integral y goes from c to d, integral x goes from a to b, f of x, y, dx, dy. So you can switch the order of integration if the integral of the absolute value is finite. There's lots of generalizations to this. I don't have to be working over rectangles. So this is an extremely useful result. In multivariable calculus, it's one of our best techniques. Is if you're having trouble with an integral, switch the order. There are some extremely difficult integrals where what you do is you take a one-dimensional integral and you convert it to a two-dimensional integral, so you can do some kind of either switching or change of variables. I will give you a warning example right now. I'll show you where this doesn't work. So whenever you see a theorem, I find the best way to understand what's going on is to look at extreme cases. Real analysis is extremely hard because you can have lots of exceptions. I'm going to define a sequence as follows. I'm going to show a double sum where I can't switch the order. If you want an integral rather than a double sum, what you do is you smear things out. So I'm going to define my function as follows, or my sequence as follows. It's going to be 1 here, -1 here, and then 0 for the rest of eternity as I go up. It'll be 0, 1, -1, 0 for the rest of eternity. 0, 0, 1, -1, and then 0 for the rest of eternity. So now what I want to do is, this is my sequence an. So I want to look at the sum, m goes from 0 to infinity, the sum n goes from 0 to infinity of a mn, versus the sum n goes from 0 to infinity, the sum m goes from 0 to infinity of a mn. So the hardest part for me is always figuring out, is m the row or is m the column? So if I fix m, I'll have, a50, a51, a52, a53, a54. Okay, that should be a column. So here, what I'm doing first is I choose a column, and then I sum everything in the column, and then I sum all the columns. What does every column sum to? So the sum of 0 is 0. Now let's look at it this way. Now I first fix a row. What does each row sum to?
0
Except for the first row, which sums to 1. So I can't switch the order of sums. How many of you have ever seen a counterexample to Fubini? How many of you have seen Fubini's theorem in Calc 3? So again, whenever you see theorems, you want to remove a condition and see what happens. If you remove a condition, typically one of two things happens. The result fails, or the proof is harder. Sometimes the proof is easier. Sometimes when you have these conditions, you look for a different way of proving things, and you look at the wrong path. So if you haven't seen Fubini's theorem, it's great to see this. It's great to see the danger and the difficulty. You cannot always interchange. Okay, so this is just a quick blitzkrieg review of integration. So we now have talked about, we want to check and make sure everything is well defined. If it's blowing up, we want to see how badly it's blowing up. One of the ideas we might want to keep in mind is, if there are blow-ups, is to look at some kind of limiting argument. All right, so now let's look at our first integral. We're integrating from 0 to pi, so there's no infinity there. Our function is bounded, no problem there. All right, things look very nice. Okay? All right, so this is probably a warm-up problem to get to really bad integration. Okay? And then there was already a suggestion as to how to do this. What was the suggestion? Integration by parts. And I like to do an overkill. So for this problem, there's really only two choices for you. What are the two choices for you? Right. So which do you think we want to do? Do you think we want u to be the exponential, or do we want u to be the cosine? Yeah, they both seem nice, actually, for this. If we had a polynomial, we would want the polynomial to be u, because then as we take the derivative, the degree would be getting smaller and smaller and smaller. But for this one, the integral of an exponential is an exponential, the integral of a cosine is a sine, and if we did it the other way, the derivative of a cosine is, it doesn't really matter that much. So I don't know how to solve this one, or I haven't looked at the solution in a while. I don't know which one is better. As an aside, here's one that's a little trickier. The integral from minus infinity to infinity of x squared 1 over square root of 2 pi e to the negative x squared over 2 dx. This is the second moment, or this gives you the variance of a Gaussian. And for this one, it is an integration by parts. And you might say, let's let u... Yes. So you might say, let's make u be x squared, because then when we take the derivative, we'll get 2x. But then the problem is you need the antiderivative of e to the negative x squared, which we don't know how to do. So what you want to do is you want u to be x, and then dv is e to the negative x squared over 2x dx. And now when I integrate the dv, I will get e to the negative x squared over 2, I think with a negative sign. And then du will just be dx. And I've now decreased the degree of this from x squared to x to the 0. So sometimes it's not always clear how you split things up. For this one, fortunately, it doesn't seem to matter. Okay. So let's do it now. Do you want u to be e to the cx, or do you want it the other way? Okay. I would have done it the other way just because I always hate remembering when I integrate cosine, do I have to put in the negative sign or not? But we can do it this way. So we want u to be e to the cx, then dv is cosine of x dx. What's the integral of cosine? And we can check. The derivative of sine is cosine, right? A lot of people amazingly make trig mistakes on this. My mnemonic is the derivative of sine and cosine are cosine and sine, and they flip order. You have to remember where the minus sign goes. If you just spell it out, minus sine, it comes down here. Okay? So this really helps me. The other thing you can, of course, do is you can draw the circle. And you can see if you're drawing the circle, as x increases, cosine is getting smaller, so its derivative should be negative. It's amazing how many people make small sign errors like this. If you can have a mnemonic, if you can have a rough idea of what the formula is, and then fix it, that's great. All right, so we've got v is sine of x. U is e to the cx du is going to be c e to the cx dx. And so we then get I is equal to e to the cx sine of x at 0 and pi minus the integral from 0 to pi, I'm sorry, right, of, okay, it's uv minus v du. So it'll be c e to the c x sine of x dx. Have I made any mistakes? Okay. What is e to the cx sine of x at 0 and pi? Just 0, right? Sine of 0 is 0, sine of pi is 0. So this term vanishes. And now we're left with this integral. How do we evaluate this integral? We do the same process again. So now u will be e to the cx again. dv now is going to be sine of x dx. I'll pull the c outside the integral. I'll then get du is c e to the cx dx. V, what's the antiderivative of sine? Negative cosine of x. And so now this integral is going to be uv, so it'll be negative e to the cx cosine x at 0 and pi minus v du, so it becomes a plus integral from 0 to pi of c e to the cx cosine of x dx. Okay? What do I get when I do cosine of pi and cosine of 0? I'm sorry? 1 and negative 1. Right? So it's not going to vanish, unfortunately. So what we get when we put everything together is I equals, so I'm going to have negative c. Now when I put in pi, I get cosine of pi is negative 1, so negative times negative is positive 1, so I should get e to the c pi. And then when I put in 0, I'll get 1. But then it's a negative 1 because I'm subtracting it and another negative 1 here. Right, did I make a mistake?
I think you put a negative on the outside and this in the negative.
Well, no, I have a negative from this. Right? Right, I equals negative c times this. And now I'm substituting in for what this integral is. So for this part, I think I've got it correct?
Yeah.
Okay. And now the next one is, now when I put in x equals 0, I'll get 1. Then I have a negative 1 because I'm subtracting, then another negative 1 here, so it becomes a plus. So it becomes plus e to the 0, which is just 1. So this is the lower bound. So when you subtract the lower bound, you get a negative sign. And then we have a negative sign here. So we have two negative signs here. So I think it's e to the c pi plus 1. Now this piece over here, what is this integral? C times I. And so we get from this, I is equal to negative c e to the c pi plus 1 minus c squared I. Okay? I'm going to erase the integration by parts and just continue so we can just keep it all on the same board. Everybody's comfortable over here? So I don't know if this method has a name. When I taught differential equations here back in 2009, we decided to call this the bring it over method. You've got your unknown on both sides, bring it over. This should remind you of how you solved equations back when you had like 3x plus 5 equals 7x minus 4. Put all the x's on one side, put all the constants on the other side. And so now we go I is equal to negative c e to the c pi plus 1 minus c squared I. So bringing it over, we get 1 plus c squared times I is negative c e to the c pi plus 1. Therefore, I equals negative c e to the c pi plus 1 divided by 1 plus c squared. When you get an answer like this, what should your first thought be? Okay, but so how would checking the derivative help us? Because this is a number, right? So I want to know, is this number reasonable? Yeah, I've written down an answer. We did 2 integration.
Plug it into the calculator.
Plug it into the calculator. Okay.
And integrate. I mean, it's going to be less than the integral of just 0 to pi of e to the cx.
Okay, good. So, right, so one thing is, let's look at extremes. Cosine is between minus 1 and 1. So the largest this could be would be e to the c pi. And then it's got an interval of length pi. So the maximum this could be would be like pi e to the c pi. And this is going to be less than that, at least in absolute value. So first thing is bounds. The absolute value of I should be less than or equal to pi times e to the c pi, which is definitely true, because c over 1 plus c squared is clearly less than 1. Maybe I have to worry a little bit about the plus 1 here, but I'm not that worried about it. So that's the first thing, is it's at least not too big. Another thing you could always do is, what should happen as c goes to infinity? What do you expect to happen? It to get bigger. And so this is getting bigger as c goes to infinity. Do you expect this to be positive or negative? You know, we have a negative number. Are you happy with a negative number? Not really. I don't like negative numbers. Should this integral be positive or negative? It should be negative. Why should it be negative?
Well, we have from 0 to 1, we have
Well, zero, we don't do 0 to 1.
0. Well, from so 0 on that interval, well, cos x is going to be negative from pi over 2 to pi.
Yeah, so here's the natural point. Pi halves. So cosine looks something like this. Right? So cosine looks like this. And the function e to the cx. So this is, cosine of x. And here's, my function e to the cx. It's really revving up. So, the area under cosine cancels between here and here, but this part is weighted by a much smaller amount than this part. So I expect the integral to be negative. In fact, I should have even done this before I did any integration. I should have just said, what do I expect my answer to look like? Do I expect it to be a positive number or a negative? So we expect negative, and the absolute value should go to negative infinity as c goes to infinity. C gets larger and larger and larger. We're just revving this up more and more and more. And it should be going to negative infinity. So this answer here, the proof that it's right was the calculation we did, and hopefully we made no errors. But it's at least reasonable. And again, as you go deeper and deeper in mathematics, or if you go into finance or whatnot, you will have very complicated expressions. You want to stop and say, is this reasonable? What kind of property should this have? One of my greatest moments as a teacher is one of my students from Brown was actually working in finance. And before they did a major investment, he was like, wait a minute, this doesn't look right. And he just tried a simple case. It turns out a minus sign was dropped. And so he got a lot of credit with his bosses for noticing that something was wrong with the prediction. You want to take a quick look and see, is this reasonable? Is this what I would expect? So the bring it over method is extremely powerful. Typically, if you're going to use integration by parts, you want to have a sine or a cosine, and then if you do it an even number of times, you return to where you start. So the idea is you want your unknown on both sides of the equation. There's only one way when the unknown is on both sides of the equation that you're screwed. What's the one way you would be screwed if the unknown is on both sides of the equation?
I equals 5 plus I.
Well, actually, it wouldn't be I equals 5 plus I. It would be I equals constant plus I, and that constant would turn out to be 0. If I has the same weights on both sides, you're screwed. Because you just have a useless equality that I is I, or I am I, however you want to phrase it. Right? So as long as you don't have the same constant, what would be a difficult constant for us this time? So do we have to worry that c squared if c is I, or negative I? So technically, we're okay if c does not equal plus or minus the square root of negative 1. Because we divided by 1 plus c squared. So you always want to be careful. If I'm dividing, have I divided by 0? And I only divide by 0 if the coefficient of I on both sides is the same. Okay. Any other questions on this one? Okay, we've got 5 minutes, which should be enough to do the second one. Okay, so the second one is we are looking at the integral from 0 to pi halves of sine cubed over sine cubed plus cosine cubed. So the first thing is, do we ever have to worry about the denominator being 0? Well, the only way it would be 0 is if sines and cosines canceled each other. Fortunately, we're integrating between 0 and pi halves. And in that region, both sine and cosine, neither one of them are ever negative. And so at least one of them will be positive. So we don't have to worry about the denominator. So everything is bounded. It's clearly less than 1 in absolute value. In fact, and it's also greater than 0. So everything is bounded. So we know 0 is less than equal to I is less than equal to 1. Or sorry, pi halves. Because the integrand is at most 1. So the question is, how would we handle something like this?
My preliminary idea was, I mean, sine cubed x plus cosine cubed x looks kind of like sine squared x plus cosine squared x.
Okay.
So I was thinking divide top and bottom by sine x. So then you have sine squared x on the top, and then on the bottom you have sine squared x plus cosine squared x times cosine over sine. So then you have 1 times 1 plus cosine over sine.
Okay, so if you divide by sine of x and try to do this, it's unfortunately not going to work out well. Because now you're going to have sine squared plus cosine squared cotangent.
Yes, but then you can cancel out the sine squared and the cosine squared, and then you can multiply by.
Why can you cancel out the sine squared and the cosine squared? Because the cosine squared is being multiplied by cotangent. It's not sine squared plus cosine squared.
Right.
So, yes?
Maybe we can try to factor the denominator into sine x plus cosine x times sine square x minus sine x cosine x plus cosine square x.
So we could try to factor, but then, so one possibility is to divide by sine. Sadly, that's not going to work well. These are good things to try. We could try to factor denominator. But now if you do that, you're going to have sine x plus cosine of x. You're not going to have good cancellation. This might lead to partial fractions. This is not going to work well.
I think you could add it to itself.
So this is one of the ideas, is add it to itself. But you want to rewrite it. So what else does I equal? It's the same as the integral from 0 to pi halves of cosine cubed x over sine cubed x plus cosine cubed x dx. And the reason is there's a symmetry point. If you look at the sine of, let me see if I do this right, minus x. This is the same as the cosine, so this would be the sine of pi halves cosine of x minus the cosine of pi halves the sine of x. Sorry, let me write this slowly. This is going to be,
Can we just do it by triangles?
yeah, I'm just trying to remember the angle identity.
Sine A cosine B minus cosine A sine
Right. So it'll be sine pi halves cosine negative x plus cosine pi halves, okay, good, sine negative x. Cosine pi halves is 0, sine of pi halves is 1, cosine of negative x is just cosine. So if I just run the integration backwards, I get the same thing. And so what we get is I plus I is the integral from 0 to pi halves of sine cubed x plus cosine cubed x over sine cubed x plus cosine cubed x dx. And this is one of the easiest integrals I can give you. I'm integrating 1 from 0 to pi halves. So you get twice I is equal to pi halves. Therefore, I is equal to pi fourths. And this is a reasonable number. It's at least between 0 and pi halves. So the idea here was to recognize a symmetry. This function was symmetric. It had a lot of symmetry about it. You may have seen this many years ago when you were looking at the integral from 0 to 2 pi of sine squared of x dx. This is also the same as the integral from 0 to 2 pi of cosine squared of x dx. So the integral from 0 to 2 pi of sine squared of x dx is just 1/2 the integral from 0 to 2 pi of sine squared of x plus cosine squared of x dx. And now we can use the idea from earlier that this is just 1, and this will just be 1/2 integral from 0 to 2 pi of 1. So we get 2 pi over 2 or pi, and thus the integral from 0 to 2 pi of sine squared of x dx is pi. And if you do a little bit of symmetry, this is the same as the integral from 0 to pi halves of sine squared of x dx, because that's often an integral you need to know. So the idea is you can frequently break these up by symmetries. It's going to be 4 times this. And I add things to itself or add a tweak to it so that things then cancel and become nice. Okay? These are really good things to know. The takeaway is that for a lot of these problems, I can't get an easy answer if I want to integrate from, say, 0 to t. But a closed form from 0 to pi halves, 0 to infinity, 0 to 1, these are often nice. So for you to have something to think about over spring break, it would be terrible if you had no really good math to think about. Think about the integral of sine of x over x. How would you evaluate that in closed form from 0 to infinity? There are several nice ways to do it. I will talk about some, and it'll be a new technique that you have probably not seen before on Monday when we get back from spring break. And it will lead to an interesting story about the dangers of being a smart ass when you're taking your general exams as a graduate student. All right.